not going to be able to finish up chapter 26, but hopefully we'll get through most of it so we can have some time to do the worksheet for tomorrow and and get through the entire chapter before the end of the week. Okay. So last time we talked about how how we can work with voltages, right? And how we can convert between voltages and electric field, right? The two things that we talked about. One interesting thing that happened that was covered in chapter 20, when we did Gauss's law, what chapter was that? That was 24, right? One of the interesting things that happened in chapter 24 was that the thing you can prove with Gauss's law is that if you had charges on a conductor, right? What happened is that these charges is going to try to get as far away from each other as possible, right? And therefore, all of the charges will actually reside on the surface of the conductor, right? Right. The example I said is that if all you guys, just went on and played like 3 hours of tennis and everyone is stinky, you're going to sit as far apart from each other as possible, right? So you're repellent to each other, right? Same thing with if you were the same charges on the conductor, right? The charges will try to get as far away from each other as possible because on the conductor, the charges are free to move around, right? So this brings up something interesting, and right? What if instead of this wobbly shape, what if we have like some triangular shape, okay? Right? The charges are going to try to be on the surface of things, right? But notice that on this part, right, there are more charges here compared to this flat part, right? Because there's just more surface area on these sharp edges, right? Right. So therefore, right, the electric field here, you can prove this with Gauss's law, right? The electric field on the surface of a conductor, I think it's just the charge density divided by epsilon naught. It could be a factor of 2, and this is going to be in like the n hat direction. So this is not an n, this is the eta, right? Sorry for the similar letters, right? So therefore, if you have more charge density here, the electric field is going to be stronger, right? Pointing directly away from the surface, right? If you have less charge density, it's going to be a weaker electric field, right? So therefore, these sharp edges will produce electric fields that are bigger. And this is why when you microwave whatever this is, when you microwave metal in a microwave, it's naturally not because it's metal, it's because it's metal, which makes it a conductor, and if you have sharp edges, right? For example, the lid of this is probably made of metal, right? And the lid probably has a bunch of sharp edges to it. And the sharp edges is where the electric field is the greatest, right? And therefore, when you have strong electric field, then you're going to start basically shooting electrons off the piece of metal, and this is where these lightning arcs happen. So what happens is that basically kind of you're creating a little lightning bolts around, and this is how you ruin your microwave, okay? So people have done this. I haven't done this to my own microwave. If you have a perfectly spherical metal, you microwave it, it's fine. Right? Because on a sphere, there's no sharp edges, right? So the electric field doesn't get spiked up on these sharp edges, okay? If you have a perfectly polished sphere, it's actually perfectly safe to microwave it, okay? I'm not sure you want to try it on your own microwave, but maybe, if you want to try it go outside in case there's fire, have a fire extinguisher ready, okay? So that's sort of an interesting thing that we actually could have talked about in chapter 24 also. But in case you do want to microwave spherical, if you want to microwave anything metal, make sure it's just nice and polished and no sharp edges on it, okay? Because the electric field always are bigger on these sharp edges, okay? So that's actually that section. We're just going to kind of talk about that conceptually. But the next thing we're going to talk about is that what are the sources of these electric potential? How do you create voltages, right? This electric potential thing we're talking about, right, is useful for us to measure but how does the power company generate these electric potential for us? Okay. Well, the way you generate electric potential is by putting a bunch of plus charges somewhere and a bunch of negative charges elsewhere, right? So how do you do that? Okay. Because if you have a bunch of plus charges here, a bunch of negative charges here, there's going to be an electric field going down this direction, right? Because the electric field starts from the positive and goes to the negative, and that's going to give you a potential difference between the two, right? Let's say I'm traversing, you know, along this path here, right? This path here, right? If the electric field is constant, right? Well, delta V across there is negative V dot whatever path we traverse, right? Let's say this is only in the x direction, right? This will be whatever the x direction of the electric field is. And if you perform that integral, then you figure out what that is, right? Okay. So how do we arrange charges? You know, so we have a bunch of positive charges in one spot, a bunch of negative charges in another spot, right? Do we just go around picking out electrons and put them in somewhere else, right? That's a little hard to do, because you're going to have to do like 10 to the 19 of them, right, for any substantial charge to build up. So one way to do this is actually using this thing called Van der Graaf generator. I think I brought it in at some point. I can bring it in tomorrow also. How a Van der Graaf generator works is basically by just rubbing things together. Right? Remember that the first week we talked about, if you rub silk against glass, right, then the negative charge will tend to stay on the glass, and then the silk will become a little bit positively charged, right? So that's one way to generate a potential difference, because by rubbing this little belt, this is basically just, imagine you just have a little conveyor belt, you just run this, and you have some object here that is actually an insulator that's just kind of rubbing against it all the time as the belt is going along. And what it's doing is depositing, by just rubbing the two objects together, you're depositing positive charge to the belt. And when the belt gets to the top here, it's connected to this metal dome, right? And then remember when you have a conductor, right, the charges are free to move. So as soon as this belt touches the conductor, the charges move to the edge of the conductor, right? And therefore you actually collect a bunch of positive charge on the top of this dome this way, right? Right? This is not a very efficient way to produce a potential difference, right? There's all this, friction and stuff like that. But this is how initially people produce this electric potential. Okay. Nowadays, we use a electrochemical process, and you guys actually are using this right now if you have a computer or a phone, right? This is through these things called batteries. Okay, so hopefully you guys have seen these objects. You got some AA's, AAA's, right? Some 9-volt battery. This is probably some sort of camera or laptop batteries that they used to be. Laptops have like actual batteries you can plug into it, but now it's just kind of built into it. These batteries were actually first made in the 1800s when people were doing a lot of electrochemistry in order to produce electricity. And the first one that was widely used, or actually still in use today in many combustion engine cars, is called lead acid battery. Okay, it's the little big battery that's in your car. Okay, the way this works is basically using chemistry to produce electric potential across things. So how does that do that? Okay, I'm going to kind of go through it kind of conceptually. So I'm not expecting. So I think the book doesn't even talk about this, but this was just an interesting point that I want you guys to learn. How does a battery actually produce voltage, right? How do I get a bunch of chemicals together and produce a electric potential across it? Okay. So a lead acid battery kind of looks like this, where there's these panels. Okay. Each of these panels are actually alternating, where you have one panel that's called a cathode, that's the negative side, right? And then there's one panel that's actually the anode, which is the positive side. I can never remember these things, but then if you think about cathode, okay, think think about cats, cats are always these mean animals, so think of them as negative, okay? Cats are mean, therefore cathode are negative, okay? So that's how I remember them, okay? What happened is that you immerse these panels in a bath of sulfuric acid, okay? Right, with some water. Well, of course acid can have water in it, okay? And what happened is that this little chemical equation happens, okay? Where there's a lead, and you put lead, the lead is actually made of the panels are made of lead. The lead will interact with the sulfuric acid to produce kind of this lead sulfate. I actually don't know what the technical name is. PbSO4. Okay. In this process, what happens is that the lead will release, basically just, well, it's going to release a hydrogen atom, which is a +1 charge, but it also releases 2 extra electrons. Okay, there's 2 extra electrons in this little reaction. So in that case, what happened is that for every time that reaction happens, you end up with a negative charge here. Right? You get 1 positive, you get 1 negative. Sorry, 1 positive, 2 negatives. Right? Therefore, you end up with a net negative 1 charge. Right? And this is happening like billions and billions of times per second. Right? So you build up billions and billions of charge, right? Just by sticking this little lead into a bath of acid. On the other side, okay, the opposite happens where you have lead oxide interacting with whatever this base is actually, right? And it also produces PbSO4. But in that reaction, you produce 3 positive charge and 1 negative charge. Okay? So what happens here is that every time that reaction happens, you end up with 2 extra positive charges. Let's see, positive, right? So what happens is actually for every reaction that happens here, you have 2 that happens on the left-hand side in order to balance out the charge. Okay? And that way, you actually built up a positive charge on this side and a bunch of negative charge on this side. Right now, you have 2 panels with opposite charge. Therefore, you produce a potential difference between them, right? Just like if we had up here, right? This is exactly what we just made, just by dunking lead into acid. Okay. So what happened is that if you were to, let's say you want to, run your radio in your car or something like that, you just connect the circuit. What happens is that then the positive charge will flow from the positive terminal to the negative terminal, running your radio, running your car motor, your starter motor, and stuff like that. Okay. I'm not going through all the details of all the equation balancing, but just to get the conceptual why it works like that. Okay. And this is lead acid battery, from the 1800s. But like your laptop battery, your lithium battery that's in your phone, it's the same concept with just a different chemical. Okay. So what these batteries are called, okay, and this is a really annoying thing. Back in the 1800s, right, they saw some charge. They're able to make these devices that pushes charges around, right? And before people understood what is actually happening, right, they call it an electromotive force, right? Because it seems like it's pushing charges around, right? So that must be a force. But they couldn't be more wrong. Well, I mean, I think I'm being a little bit technical about it. So what they call when you have a battery, usually a drawing of a battery is just with a plus and a minus here, right? They call this an EMF, meaning electromotive force, okay? But this force is not a force, okay? And this is always confusing to students because the electromotive force is not a force, it's a voltage difference, right? So this has some dB of let's say 1.5 volts for a regular battery. The electromotive force is that 1.5 volts. Okay, so what I usually call it is the electromotive voltage instead. Okay, instead of force. Okay, no one else use that, so don't use that outside this class. Okay, but the electromotive force is a voltage, not a force. Okay, so it's important to note that. Right. So you can think about these batteries as like kind of charge moving positive charge from one end to another, right? So because that we kind of ignore the negative charges because even though those are the actual things that are moving, when people first started thinking about batteries, they thought positive charges that are moving, right? That was just another mistake that, thanks to this guy named Benjamin Franklin, right? Thought, oh, this must be positive charge, right? That's moving around. Anyway, so you can think about battery as kind of like if you place a charge at the negative end of the terminal, right? The battery is going to increase the potential energy of that particular charge until it gets to the positive terminal, right? So if this battery has a change difference in potential of 1.5 volts, right? The change in potential energy for some charge Q is going to be this 1.5 volts times whatever that charge is, right? Okay, remember? So you can model basically any battery as just something that increases the potential energy of charges as it goes through it. Okay? So what you can do is stack multiple batteries together. So let's say you want to run a flashlight, right? This flashlight requires a 3-volt potential in order to work, right? But you only have 1.5 volt batteries. But what you can do is if you stack two 1.5 volt batteries together, right, the net potential you go from 0 to 1.5, then you go 1.5 to 3, right? And that's how you get to a net potential difference of 3 volts in order to run your little flashlight, right? So, so the equation to figure this out is that if you have some batteries in series, right? Series meaning you have one after another, okay? The difference, the change in potential is just the sum of all those different potentials, right? So if you have two batteries like this, you have 3 batteries, 4 batteries, 5, you can have as many batteries as you want. What if I arrange my battery this way, okay? So this is just another poll question. We can do a raise of hand. What if I arrange my battery this way, where I have a 3-volt battery pointing to the right, a 1-volt battery pointing to the left, and then another 3-volt battery pointing to the right? What is the electromotive force provided by this entire series of batteries? Okay. Give it maybe 10 seconds for people to figure out what the number should be. Okay. Anyone thinks it's 2 volts? No? Anyone think it's 3 volts? 4 volts? How many think it's 5 volts? Okay, so most of you figure out it's 5 volts, right? Because, right, what you can do is start here, right, and you can pick the 0 point to be anywhere you want, right? You start out at 0 here, you get to 3 here, right? But this is in the opposite direction. Instead of gaining 1, you actually lose 1, right? And then you go across here, you get to 5, right? So the total is actually 5 because I put one of the batteries in the opposite direction, right? That's why when you put your batteries in, whatever device you're doing, if you put one of them in the wrong direction, it's not going to work, right? Just because one of the batteries in the wrong direction. Okay, so I think I'm out of time today. It took a little longer to do the worksheet than usual. So we'll talk about capacitors tomorrow, and we'll see how far we can get, and we'll see how the worksheet comes out, okay?